So now we're going to talk about the law of sines. In the previous section, we talked about the right angle trigonometry, and our discussion led to the to defining trig functions, the six trig functions, as ratio of sides of a triangle. Remember, before that, we defined the same trig functions as the points, coordinates of a point on a unit circle. So this is transition from definition from the unit circle definition to size of a triangle. So from now on, I tend to talk about these trig functions in terms of ratio of sides of a triangle. Now, the law of sines is going to help us solve triangles. So what do we mean by solving triangles? Well, solving triangles, that means all sides are known, all three sides, and all three interior angles are known. So 6 pieces of information would be, if we know those 6 pieces of information, we say the triangle is solved. Now, for this work, we just came out of a right triangle trigonometry. That's pretty easy. For this section and the next section, the triangles we work with are oblique triangles, and that's my triangle symbol. We're looking at oblique triangles. So what are oblique triangles? Oblique, this means that none of the angles, let me write that, none of the angles are right angle or 90 degrees. So in that case, the triangle is an oblique. So it could be, for example, 60, 60, 60. It could be 15, 90, and whatever the rest is to make it 180 degrees. All right, and keep in mind the sum of interior angles in any triangle is 180 degrees. We'll still keep that in mind. Now, so we have a number of configurations here before we actually cite the law of sines. So one possibility is that we are given one side and 2 angles in any triangle. One side, 2 angles. Okay, any 2 angles. So for example, I could have a situation like this. I'm given, again, one side, it doesn't matter which side. So let's say I'm given this side, and I'm given this angle, and I'm given this angle. Or the fact that I'm given 2 out of 3, then this third one I can easily find, right? The third angle. So if I have this configuration, any 2 angles and any one side, I can use the law of sines. Okay, so for this, we use law of sines, which I'll state it in just a moment here. So that's one configuration. One side and any 2 angles. And the other configuration here is that we have 2 sides and an angle opposite one of them. Okay, let me put 2 sides, an angle opposite one. And this is the more involved case. In fact, this is called the ambiguous case because a number of things could happen. Okay, now for this configuration, by the way, often we say we have side, side, angle. So you have 2 sides. Here, angle is opposite either first or second one, as long as it's opposite one of them. The one I have above, we have one side and any 2 angles. So for this one, in terms of shorthand notation, here I have angle, side, angle. So I have 2 angles and the side is included. So for example, it looks like this. You have angle, angle, and this is the side between them. Or you have a side and 2 angles. Again, doesn't matter. As long as you have 2 angles, that other side doesn't matter if it's adjacent, opposite to one of them. Okay, but the latter one, this one that I just did, 2 sides and an angle opposite one, this is the ambiguous case. So how is this going to look like? For instance, let's say I have, here's one side, here's another side, and this is the angle opposite one of them. And there you have it, something like this. Okay, and that would be this configuration. And for both of these again, we're going to use the law of sines. Okay. Now there are two other cases that we'll take on the next section, and that's if we have two sides and an angle that's included between them. So I have, notice the difference now would be something like this. Let's say I have a side, and the angle is included. For that, we use the law of cosine. See, that's a different configuration than the one I have here. Okay, or if I have just, let's say, three sides, side, there is no angle in there. As long as, for the law of sines, we have to have the angles. Law of cosines, we don't have to. Okay, so how are we going to work this one? Let's actually now state the law of sines. So this is the law of sines. The law of sines says that for any triangles, as long as we have these sides, and I'm going to label my sides. Remember, this is an oblique triangle, so there's no right angle in here. Let's agree to this. I'm going to label the vertices A, B, C. The side opposite cap A, we're going to call it little a. Side opposite capital B, we're going to go little b. Side opposite C, we're going to go little c. And as far as the angles go, let's say angle A, we're going to go alpha. For B, I'm going to go beta. For C, I'm going to go gamma. Okay, so this would be the triangle that I'm thinking of. And the law of sines now. The law of sines, which is very useful, is given by. The law of sines says that sine of the angle A, okay, divided by side A is the same as sine of angle B over side B and sine of angle C over side C. And I'm going to forego the proof of this in the interest of time, because I'm sure you can find the proof in any trig textbook. It's not complicated, straightforward. But so again, in the interest of time, I'm going to forego the proof of the theorem. Now, this is kind of interesting because we have like a set of equalities. So there's actually, you can rewrite the law of sines using three equalities. You can pair any two, and there you go, and do these. Then you can create three sets of equations out of this one. All right. Now, because this is, as you look at it in terms of pairs of equations, then we have ratios that form a proportion. And here's what I mean. Let's say I have a to b is equal to m to n. This is what we call a proportion. Well, if we have a proportion, then we can actually write it in another form of a ratio in this form, right? Let's say I have 2/3 is equal to, I don't know, 4/6. I doubled up on top and the bottom. So if I invert both sides, I get 3/2 is equal 6/4. So that's what we can do with a proportion. And the point I'm trying to make is this. Sometimes, if we need to, we can actually write the law of sines in terms of a over sine A equal to little b over sine B, and so on. You see that? So from time to time, I may do that for application problems. All right, so that's what the law of sine is. Okay. Now, let's see. So, and we also remember we're coming to this in terms of the measure of the angles. We know that alpha plus beta plus gamma, these angles measure 180 degrees. So we know that again from the Euclidean geometry. Now, the case, let's take a look at the case where we have side and angle opposite one of them. Okay, this is the ambiguous case again. Let's see what makes it ambiguous. Well, if I have, let's say I have a triangle and I'm given this side, that's given side. And here's the angle, and remember we have a side opposite one of them. Suppose that's the side opposite not opposite one of them, opposite the angle. So I have two sides, right? One side is opposite of the angle A. Now, in order to determine whether a triangle can even be formed here, okay, can even be formed here, well, if this side, as you can see, if this isn't long enough, I cannot even close a region, right? As I strike an arc of a circle of center at, say, O, notice no matter how I rotate that side, I cannot close the region, right? And by region, I mean this: I cannot create a polygon, right? Therefore, if the length of the side opposite, now let's label these as, call this A, and this one is B. Remember, side A is opposite angle A here. All right. And therefore, the minimum tolerance to create even a triangle is when the opposite side must be of height h, right? Which actually touches this third side. All right. So we need to determine what's the minimum tolerance to even have a triangle. And that minimum tolerance, by the way, will produce a right triangle for us. Okay. So let's write this one. All right. So we have, if A is equal to H, then the result's going to be one right triangle. Now, how do we determine H? Well, if I look at the tangent of, I'm going to move A actually on the outside now and call this alpha. I'm using this triangle notation here. Okay, so tangent of alpha, which is ratio of opposite to, actually, let's not go tan because I don't have adjacent side. Let's go sine. I can use sine alpha as h over b. From this, I can solve for h. Remember, once two sides are given, so I know the measure of b if I need to use it. B sine alpha. There you go. This is the minimum tolerance that's necessary in order to even have a triangle. All right? H has to equal to B sine alpha. And in that case, again, we have a right triangle if A is going to be less than H, right? That's the case where the side cannot form the polygon, cannot form a triangle. So if A is less than H, therefore, there is no triangle possible. The very first thing we need to do is do, in fact, this check. Do I have no triangle? Do I have one right triangle? Or, now the case beyond this is going to give us chances are two triangle, depending on angle alpha, by the way. Here, alpha is acute, okay? So alpha here is less than 90 degrees, by the way. Okay, now, the case where alpha is acute and A exceeds H. Now, remember, if it's equal H, you get one right triangle. If it's less than H and no triangle, what if it's bigger than H, but less than B? That's important. Okay, now B comes into play. In this case, we have two triangles. Again, if the angle is acute, depending on the relative size of the side and the minimum tolerance, and side B, we can have 0, 1, or 2 triangles. Now, the case where A is less than or equal to B, in this case, let's say alpha is now greater than 90 degrees. In other words, alpha is an obtuse angle. Okay, if alpha is an obtuse angle, then we have something like this. Let's say here's the measure of alpha, and let's say that's side A now. This is B. Okay, and again, if I strike an arc of a circle here, notice I cannot create a triangle. I cannot close that region, right? So A is less than or equal to B. There's going to be no triangle possible. No triangle. And what if A is greater than or equal to B, but the measure of the angle is acute? Okay, so in this case, or actually, let's say this time now, A is greater than B. Okay, A is greater than B. So if this is B, and the angle, of course, is obtuse. Okay, this is an obtuse angle. A is greater than. There, now it is possible to close the region and have a triangle. So A is greater than B. This one yields one triangle. See how so many possibilities? There are 5 possibilities here. Right triangle, no triangle, 2 triangles when alpha is acute. And then in the case of alpha being obtuse, we have these 2 possibilities. Okay. So let's take a look and see. And also, by the way, the case, another one, let me think of another one. What if A is greater than or equal to B? Well, the case where, let's say, in here, this is B, this is A, and they happen to be equal, and this is the acute angle, A, right? So this is an acute angle. Well, if they're equal, then we have one triangle. Okay. And I think that covers all possibilities. Now, how are we going to do this? Maybe I can summarize all this in a chart for you. Let's do that because it's all over the place. So here's a measure of angle A, okay, whose opposite side is given. If it's acute or if it's obtuse, okay, we're going to create our table here. If the angle A is acute and A is, remember, little a side opposite angle A. If A is less than H, we said there is no triangle. Okay, if A is equal to H, then there is one triangle. And if A is greater than H but less than B, then there are 2 triangles. There we have that part. Now, when the angle is obtuse, if A is less than or equal to B, then there is no triangle. Okay, notice in here I said they're equal, but the angle was acute. That's when I had one triangle. Right here is a case where we have no triangle if it's obtuse. And the case where A is greater than B, then we have one triangle. All right. And that's how we're going to summarize it. So there are 5 cases, and hence this is called the ambiguous case. All right, let's take a look at some examples here. In this example, let's say in the first example, suppose angle A is 40 degrees, angle B is 40 degrees, and side C is 2. So here's a case where we have angle, side, right? We are given 2 angles and any side. Well, if AB are 40 each, then measure of angle C, and this is side C is like little c. This is cap C. Angle C is 180 minus 40 plus 40 is 80, so that is 100 degrees. Good, and we were able to find it. And let me do this. Suppose this is 40, this is 40, and here's A, here's B, that's C. Well, it's 100 degrees. There you go. That's 100 degrees. Now we're given C is 2. There. Now we can find a measure of A and B. They're going to be equal because it looks like I have an isosceles triangle, right? Because it has two equal sides. Because my base angles are each 40. That's why. All right. Now let's take a look at this one now. So for the law of sines, I will need to determine a little a and b. Now here's the version of law of sines that I'm going to go with. Okay, I'm going to go a over sine a is equal to little c over sine capital C. And from this, multiply, cross multiply or multiply both sides by sine a. So I get c sine cap a over sine C. And that should solve for A, right? C is 2, sine A is 40, and sine C, that would be sine of 100 degrees. If I did the calculations correctly, I get 1.3, the measure of the length. Now, you know B is going to be the same, but let's say just to make sure, we're just going to run the law of sines again, this time with B. And this is going to be C over sine C. So from this, B is equal to multiply top bottom this time by sine capital B. So it's little c times sine capital B over sine capital C. C is 2 sine 40, and it looks exactly like the equation directly above what I'm writing. Right? They look the same. All right. So we have solved the triangle again. We have the measure of all three sides and all three angles. That's what solving the triangle means. Perfect. That one is done. Let's take a look at another example. So this example, suppose I'm given now two sides and an angle. Okay, the side is opposite the given angle. So for this one, let's say my B is 4 and C is 6 and capital B is 20 degrees. All right, now let me set this one up. The measure of angle is 20 degrees, so that's 20 degrees. Here's capital B. Remember, the side opposite is little b, so that's going to be 4, and let C be the other side. Okay. Again, B is 4 is less than 6. Now the question is, do I meet the minimum tolerance? Remember, in order to have at least a right triangle is the minimum tolerance H to even have a triangle. So I need to determine the value of H, and we're going to use sine of 20 degrees, which is H over 6, opposite to hypotenuse. From this, we get H is 6 sine 20. Now, sine of 20 degrees, you got to use a calculator on this one, right? And I did. And I got 2.05. Okay, so that's the minimum tolerance to even have a triangle, a right triangle. B is 4. B is 4, so we're good. We definitely have a triangle. And because B is greater than H, now we're thinking, okay, how could this be? Well, one possibility would be such. Let's say this is 4. Okay, and here's one triangle, and that's 4. This angle is 20 degrees, and the side is 6. Correct? Now we can use the law of sines. This is B, that will be capital C, that's little a, cap A, and the side opposite is little a. Now I'm going to use the law of sines with C. Sine cap C over little c is equal to sine of 20 divided by 4, right? Sine of the angle divided by the side opposite the angle, in this case 4. Now from this I can actually determine sine of cap C is little c times sine, I'm multiplying top bottom by c. I'm sorry, not top bottom, I'm multiplying both sides by little c. And this will give me c is 6, sine 20 divided by 4, and the value ends up being 0.513. That's sine of the angle, not the angle. So how do I find C? I have to use my calculator by definition of inverse. C would be the arc sine of 0.513. Okay. Now, this is a real number. This is a real number. So arc sine of that, my calculator can handle this, and it gives me 30.87 degrees. So that's the measure of angle C, right? We found this angle to be 30.87 degrees, and once we have that, then we can find the measure of angle A, right? So angle A is going to be 180 minus 30.87 minus 20. All right, and the measure of this angle is going to be 129.13 degrees. And all we got to do is find little a, correct? Because we know B and C, we need to find A. So how are we going to find A? Well, I'm going to do the law of sines in the form of A over sine cap A. I can use B over sine B, or you can use C over sine C, doesn't matter. Multiply both sides by capital sine cap A. So this would be B sine A divided by sine B. And then put the specifics, the numbers, that's 4 sine 129.13 degrees divided by sine of 20 degrees. And the length of the side A turns out to be about 9.1. So we have solved the triangle. One solution is A is 9.1. B, what was B? B was 4, right? We were given that. C, we were given 6. The measure of angles are capital A, 129.13 degrees. Capital B was given to be 20 degrees. Cap C, we found it to be 30.87 degrees. And there we have solved that triangle completely. Now, here, by the way, here's a case where we have 2 triangles possible. And check this out. There you go. If the measure of the angle is acute, that was 20 degrees for us. And A is bigger than H, which makes the triangle possible, but A is less than B, right? We were given A is 4, B is 6. So there's actually 2 triangles possible. Okay, so how do I find the other triangle? Well, the other triangle could be done this way. Let me do this. So right now, this is what we found. True, this is 4, that's 6. The other possibility is, this could be, the side could be configured this way. Again, if you strike an arc of a circle centered at, say, O here, you can see the circle, the radius of the circle. When you draw it, it crosses the opposite side of that triangle in 2 places. Right now, this is what we found. This was 30.87 degrees. The other triangle, the other possibility for the triangle is right in here. You see that? So we can now work with this triangle. Now, with respect to this triangle, because these two sides are 4 each, right? So we have an isosceles triangle, means the base angles are the same. This angle would be 3087. So that means the supplement of that angle is also going to be an answer, right? The supplement of the angle is 180 minus that. Okay, and what do we get? 180 minus 30.87. We get 149.13. These two add to 180. Perfect. And here's our other triangle. The second triangle, call it, is going to be this one. Right in here, where this is A, which is not A, we labeled it as B, sorry. So that's 4, this is 6. This was 20 degrees, the measure of the supplementary angle, 149.13. And now we can find the measure of this angle, right? Which we called angle A. So angle A is now 180 less 20 less 149.13 degrees. And that angle is going to be 10.87 degrees. And what we got to do is now find little a using the law of sines in this new triangle. And we're going to go little b over sine b. Multiply both sides by sine a, and we say b sine a divided by sine b. And that should solve it for us. So that's 4 times sine of 10.87 degrees divided by sine of b is 20 degrees. Now, do this on the calculator and you get a to be 2.2. And there we have that one. This is 2.2, and we have solved that triangle. So it is, again, an ambiguous case because so many things could happen. I'm hoping that the chart I have up here is going to help you. This chart is going to help everyone try to sort this out. Okay. And so there you have it. Now, when we do the applications are easier to work with because they're just straight law of sines, and we should be able to solve these application problems easily. So let's take a look at an application here. So here it is. Let's try this problem. So according to this figure, it says to find the length of the span of a proposed ski lift from P to Q, a surveyor measures the angle DPQ to be 25 degrees. That would be this angle near the base, down here. That angle is 25 degrees. And then walks back a distance of 1,000 feet to R and measures angle P or Q to be 15 degrees. What is the distance from P to Q? Okay, so that's what we want to know, the distance from P to Q. This distance, call it D. All right. Well, the fact that this angle is 25 degrees near the base, we can find the angle P. This angle is going to be what? A supplementary angle, so it's 155 degrees because these two form a straight angle. So the supplementary to a 25 is going to be 155 degrees. We have that one. Now, once we have that as 155 degrees, then we can actually find the measure of this angle, couldn't we? This one is going to be, that's angle Q, right? So angle Q is going to be 180 minus 15 minus 155 degrees, and that would be 10 degrees. Okay, so we have this angle figured out, that's 10 degrees. Pretty much all the angles are known, so we can just use the law of sines then in this case. And using the law of sine, I'm going to use d, the distance that we are seeking, divided by sine of the angle opposite that would be sine of the 15-degree angle, right? Opposite to d, that angle is 15 degrees. Okay, that should equal to the known side of 1,000, this over the sine of 10 degrees. Over sine 10. And you multiply both sides by sine 15 degrees, we get 1,000. Sine 15 degrees divided by sine of 10 degrees, and that's going to equal to 1,490.48 feet. So that will be the distance, or the span as it calls it, the length of the span of that ski lift. And there we have that one. Now let's before we look at another application, also let me just do a couple of examples here where one, let's say there will be no triangle. Okay, so let's say I have A is 3. I'm going to make B to be bigger. B would be 7. I'm going to let angle A to be 70 degrees. Okay, so according to our labels, this is 7. This is a measure of the angle 70 degrees, and the side opposite is 3. Okay, so remember the minimum tolerance is H, and H is given by, if you form the this is H, by the way, right in here. So I can say that sine of H is the ratio of, I'm sorry, not sine of H, sine of 70 degrees is opposite H over the hypotenuse 7. So H would be 7 sine 70 degrees. Using my calculator, I get minimum tolerance of 6.6. And this time I'm going to say since 3 is less than 6.6, therefore no triangle can be formed. See that? Again, no matter how you revolve that side, and this is going to create a polygon, a closed geometric shape. Okay, now let's take a look at another example. This time, suppose I have something like this. Let's say, let me just draw this thing out. Suppose I have an obtuse angle. Let's make this 95 degrees. I know it's probably less. There you go. I exaggerated. There, that's better now. That's closer to 90 degrees. Okay, 95 degrees. So it's obtuse. And suppose now I'm given this side is 4. Okay, and there you go. This is 4, and this side is B is, call it 5. Okay, or without labeling any name, let's just call this side 5. Now, again, if I strike an arc of a circle here, I will not be able to close that region. Okay, because again, the radius is 4. Let me make it a little more realistic. Suppose that's 4 there. Now that when I revolve this, you can see I cannot close that region and create a triangle. So here's a case where I have 4 is less than 5. Okay, and again, no triangle is possible. And let's do another possibility here. Let's say this time, suppose I have something like this. Let's say this side is 8 and this side is 3. Again, 3 is less than 8. The angle is obtuse. Okay, and suppose that's 125 degrees now, something much bigger than 90. 125 degrees, and again, here's a case where 3 is less than 8. I have an obtuse angle, and for this, again, no triangle is possible. What's important is that we have obtuse angle, and the side opposite the angle in both cases is less than the known side, the other given side. All right. Let's take a look at another application. So let me bring up this application next. Okay, in this example, we want to find the lean of the Leaning Tower of Pisa. The famous Leaning Tower of Pisa was originally 184.5 feet high. At a distance of 123 feet from the base of the tower, the angle of elevation to the top of the tower is 60 degrees. Now, in this drawing, by the way, because I don't know, some of you may interpret this distance to be from the base of the tower to be 123, but actually this is the distance right there. All of that distance is 123 feet. Okay, so suppose that's the case. From the base of the tower, the angle of elevation we're given, we want to find the angle RPQ. Okay, that would be this angle, RPQ, indicated in the figure. Also find the perpendicular distance from R to PQ. Okay, that is this distance we want to find. Call that H. So we want to find angle P, and we want to find out what H is. Those two unknowns. All right, so let's actually, to find H, let's see, we can find H by forming tangent. So what triangle I'm looking at actually is this triangle. Okay, I can do a tangent, but when I do tangent, I actually don't know this angle yet. So let's hold off on that part. All right, so okay, got it. Let's do it this way. We're gonna do the law of sines. Okay, how are we going to do the law of sines? We're going to do the law of sines with this triangle. This would be 60, right? Given this is 184.5. And we can actually find the measure of this angle. This is R. Remember, we're given side opposite is 123 feet. Oh, good, that should do it. Let's go sine of R divided by 123 is equal to sine of 60 divided by 184.5. Okay, so from this, we get sine of R is equal, multiply both sides by 123 times sine 60 divided by 184.5. And sine of R ends up being 0.577. Then if you do inverse sine, R would be inverse sine of 0.577. And that's going to be 35.26 degrees. Okay, now I can find the measure of angle P, right? So P, angle P is going to be 180 minus 60 minus R, which is 35.26 degrees. And the measure of that angle is going to be 84.74 degrees. Okay, so how am I going to find H again? The tangent I said earlier, tangent of P is going to be H over 184.5. I'm looking at this triangle now. Okay, and let me draw that. I'm looking at this triangle. Here's H, this is 184.5, and this is the measure of angle P, that. All right, and therefore H, cross multiply, H is 184.5 times tangent of P, which is 84.74 degrees. And doing this one, we get, on my calculator, I got 183.71 feet. So that would be the vertical distance right? Perpendicular distance from R to the ground, 183.71. Very close to 184.5. Okay. So therefore the lean isn't that bad, right? It's supposed to be straight like that, 90 degrees. It's actually 84.74 degrees. So it's leaning about 5 degrees. Okay, from the top. Perfect. So here's the example. Let's take a look at another example here. This will be the last example for us. So let's take a look at this. This is a very interesting one. The problem reads, one of the original 7 wonders of the world, the Great Pyramid of Cheops, was built about 2580 BC. Well, a long time ago. Its original height was 480 feet 11 inches, but owing to the loss of its topmost stones, it is now shorter. Okay. Find the current height of the Great Pyramid using the information given. So let's try to work this one. Now for this one, we're given a couple of triangles here, right? So let me draw these triangles away from the figure itself. All right, so this is what I mean. I'm gonna draw a triangle this way. So this is the height that we are seeking, call it h. And this one is the 40.3 degree angle. And this other one, the distance of the first one is about 200 feet from the base of, this is the pyramid itself. Okay. And the second one is going to be, let's draw it like this. Like that. And this one is about 100 feet. So this distance is 100 feet. All right, so we clearly can form 2 triangles, my blue triangle, and then I have this longer triangle. Let's make that a red triangle. There, we have the blue and we have the red triangles. Now, in these 2 triangles, let's do the red one. I can do tangent of 46.3 degrees as, or as tangent of, it's 46.27 degrees. Right, 46.27 degrees, that's this one. That's the measure of the angle, 46.27 degrees. Okay, so we can do tangent of that. And, the distance, let's call this horizontal distance d. That's from here to here. Okay, d is that distance. So it's going to be h, the altitude of the pyramid, divided by d plus 100. Correct? Again, if this is d for the blue triangle, there, that's what I just found. The side, the length of the side is 100 plus d. So from this, I can get an equation in h, cross multiply. I'm going to get what? Tangent of 46.27 degrees times d plus 100. And then I can look at my red triangle. So right, using the red triangle, I can say the tangent of 40.3 degrees. That's this triangle. And I can form a similar ratio. Tangent would be h over this time d plus 200, correct? Because for the red triangle, that side is d plus 200 now. For the red triangle. And I can solve for h, right? Cross multiply, and I get tan 40.3 degrees times d plus 200. So what this will do in effect, it will give me two equations and two unknowns, right? So one way, instead of setting up a system and solve this as a system, I can do this. Well, it's the same height, right? Regardless of which triangle I use. It's the same height. So I can set the heights, the equation for the heights equal to each other and solve it for d. So that's what I'm going to do. Rather than solving two equations, two unknowns. Two unknowns would be d and h. So h from the first equation is this, right? And because it's the same height, I'm going to set it equal to the second equation times d plus 200. All right. And then I can distribute, right? Let's distribute and use my calculator. So distribute on the left, I get d times tangent of 46.27 degrees plus multiply 100 times tan 46.27. You get 104.53. And on the right side, the same thing. Multiply d times tangent of 40.3 degrees plus do 200 times tan 40.3. You should get 169.61. Okay. Now I'm going to collect my d terms on the same side. So that means I have tan 46.27 degrees times d minus, bring this term on the right, move it from the right to the left. I get minus tan 40.3 degrees times d equals, then I go 169.61 minus, move 104.53 to the other side. All right, and so this will give me, I can say d is equal to, on the right side, I get 65.8, and divided by the coefficient on d, which is tangent 46.27 degrees minus, I'm going to use a calculator here in a moment. I'm just postponing the inevitable 65.08. And now using my calculator, I got a d to be 329.9 feet. Okay, but that's not what the question asked for. The question wanted the height, right? I found d, so I can actually now say I can use either of these two equations to solve for h, the height of the pyramid. Okay, and let's say I use the first one, 46.27, tangent of 46.27 degrees times d plus 100, that's 329.9 plus 100. And that will give you 429.9 times tan 46.27, and the h that I get is 449.4 feet. So the height is smaller. It looks like the height has shrunk due to losing the top rocks. 449, call it 450 almost, versus the initial 480. So it's lost about 30 inches. Okay, due to erosion time. All right, and I think that will do it. We are done with this section. We only got one more section to cover in this chapter, chapter 8. Our next section would be the law of cosines. So there you have it. We are done with the law of sines. And thank you for watching.